Hello everyone, my name is Michael Franklin Bobda and I'm going to present you our paper entitled A Word Representation to Improve Name Entity Recognition in Low Resource Languages. This paper has been accepted to ANLP 2019. The outline of my presentation is the following. After the introduction, I will give a brief state of the art, following by an overview of annotation projection. And then I will show you the word representation we are proposing in this paper, following by how we use it to improve name entity recognition in low resource languages. I will show you the experiment we did and conclude this presentation. For introduction, let's define what is name entity recognition. It is a subtask of natural language processing that aims to identify and classify expressions such as person names, organization names, and location names from text. Let's see it in an example. Michael Franklin is not moving to Grenada for the ANLP workshop. Suppose you have this sentence and we want to do name entity recognition on it. So the name entity recognizer system have to identify Michael Franklin as a person name, Granada as a location name, and ANLP as an organization name. This task is used in many other tasks of natural language processing and others. For instance, in automatic translation, it is highly used. It is also used in recommender system to extract item from user comments, also for co-reference resolution and other tasks. In the state of the art, we have role-based approaches that use handcrafted rules. That means humans or linguists are the one that build rules that are used to do name entity recognition. These approaches are accurate and very interpretable because we always know the reason, or we are always able to explain the output of the model. But it is time consuming because handcrafted rules are not easy to define and it needs linguistic knowledge. We also have machine learning approaches that are trying to overcome the limitation in the rule-based approaches. So in machine learning approaches, the rules are automatically learned from data. These approaches are easier to generalize, but they miss interpretability. We are not able to always say why the model output a result, but sometimes we can. We also have hybrid approach that try to combine machine learning approaches and rule-based approaches. So the limitation of the method we found in the state of the art is that they cannot be applied to low resource languages because they need annotated data. These annotated data are not available in low resource languages. So one solution is annotation projection. What is it? It has been introduced in 2001 and the idea is simple. It is based on a parallel corpus. A btext is a parallel corpus made of two languages. In this corpus, each phrase is written in two languages. Usually we have a rich language and a low resource language. The rich language have a lot of annotated data available so that we can train a model to automatically annotate this side of the corpus. but the low resource size of the corpus do not have annotated data. So the idea behind annotation projection is to train a model on the rich side of the corpus, annotate this side of the corpus, and then align the word from this side with their translation to the poor side, so that we can use the projection that we get in the rich side on their translation in the low resource side of the corpus. So the word representation, we want to find a space that is common to both language of the parallel corpus. Why is it important? Because if we can project the word from both language to a space where they are the same, that means that a model that we train on the rich side could be used to classify data from the low resource size of the corpus. So by the observation that each expression and its translation always appear in the same B phrase, Zenaki and al. Define what they call the distributional signature of a word, that is a binary vector of size n such that the component number e is defined as being 1 if w appear in the B phrase number I and 0 otherwise. For illustration, suppose you have a btext of three B phrases. This btext is composed of phrases in English and their translation in Ewondo. Ewondo is a Bantu language from Cameroon. You don't have to know Ewondo to understand the illustration here, because we have used the same color for each word and its translation in the other side. For instance, you have Jesus that is translated to Jesus in Ewondo. You also have David that doesn't change. The same stand for Abraham. Using the previous definition from Zenaki, we know that the representation of Jesus is equal to the representation of Jesus, which is 110. However, its observation doesn't hold everywhere, since the representation of Christ is different from the representation of Christus, which is the translation of Christ. That is not a problem with the observation, but it's a problem due to human. When we say Jesus Christ, it's quite implicit. When we say Jesus, or Jesus, it's quite implicit to understand that it's we are talking about Jesus Christ, and sometimes Christ is omitted. That's why these representations are different here. So our new representation is based on the hypothesis that name entities are less frequent in text than other expression. And using this hypothesis, we define the descriptional signature, and we say that instead of using 1, we are going to use a real number. This real number is just the quotient of the number of words in the corpus, that is the total number of words in our corpus, divided by the number of occurrences of the word W in the corpus. With this definition, we want the vector representing name entity to be far away from the origin, from the null vector, and we also want the vector representing non-name entity to be very close to the null vector. And how do we use this representation to do name entity recognition for low resource languages? So we compute the representation of each word in our corpus. This is the signature of the word in the rich side and in the low resource side. We then train a neural network on this rich side of the corpus, only on the rich side, since the 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 poor side of the corpus is not annotated. We cannot train a model, a supervised model here, so we train only on the rich side. We then use the train model to annotate the low resource side of the corpus. Since the descriptional signature of each word are the same for each language, we know that our model can annotate this side of the corpus. The strength is that no word alignment is required. There is no need to choose a similarity measure, since the network will choose one itself during training depending of data, and we do no assumption on the target language. Our experiment, we to experiment to evaluate our approach, we had a problem because there was no data available for Ewondo, our low resource languages. So we extracted data from the site www.bible.com and manually annotated it using BRAT. We extract exactly 210 verses from the Bible. That is more than 4,000 words in English and Ewondo, and more than 900 words. This 10 words. Now, since the site bible.com has not been built, did not take alignment into account. Sometimes we have a verses or a phrase in English that is translated in two phrases in Ewondo. So we normalize this by using the verses as phrases. So we suppose that we have 210 verses or phrases in our corpus. We also try to evaluate or to validate our hypothesis, and we see that the percentage of non-name entity in our corpus is more than 80%. That is a validation of our hypothesis. For experimentation, we use Keras with TensorFlow as backend, and we train on 10 epoch using 10-fold cross-validation. We use a neural network that has two hidden layers. The first one have 640 neurons, and the second one have 160 neurons. We stop the training if the validation loss is the same for two consecutive epochs. The results we got were impressive. We see that our signature increases the model performances a lot. The baseline for us is the same algorithm that we defined previously, but using the signature defined by Zinaki and al. So we show that even if the representation used by Zinaki have worked very well for POS tagging, our representation is better for name entity recognition, and we can see that the increase in precision, F-score and recall are very, very significant. So to conclude, our representation of word is more suitable for name entity projection, and using it, we project name entity from English to Ewondo. This is a first work ever done with good precision, recall, and accuracy. As future works, we want to test our representation on other NLP tags. For example, we want to see if our representation is also better for POS, part of speech tagging projection, than Zinaki L representation. We also want to analyze the misclassification error. to understand why some words are not well annotated. And finally, we want to test on data set from other domains. Here we do think that the Bible corpus is quite limited, or is not quite varied, so we want to test on other other domains data set. Thank you.